to show you something that you are going to need for Chapter 5, and then be able to come in on Monday and start Chapter 5 fresh, all right? So right now, when we were factoring quadratics, these degree 2 expressions and equations, quadratics has a very specific technique of factoring. There are a few other techniques to factoring that you are going to need to know when we get to Chapter 5. And I think it's going to be much easier for you to see them now before we start Chapter 5 instead of throwing you into Chapter 5 and seeing them for the first time, okay? So I need to show you a couple different factoring techniques today. So what I'm going to do is, after we are done with them and you see the techniques, it's your decision. I'm going to post a homework assignment for the weekend that will be optional. If you would like to practice these new techniques a little bit more, you can go into the homework. You can do a couple problems, you can do all of them, you can do none of them. It's your decision. These are just techniques, though, that you're going to have to be aware of when we start working in Chapter 5. Chapter 5 is going to start with exponent rules that you should know from Algebra 1, and then it's going to go into more nonlinear equations, higher degree equations. We just spent 3 months working with degree 2s. Now we're going to see degree 3 equations, degree 4 equations, degree 5 equations. So obviously, the higher the degree gets, the more complicated they get, the more complicated their graph gets, the more answers their equations are going to have. So again, it would make sense that we're going to have more ways to factor, to break things apart, all right? So let's go over a couple of these techniques, and then we can see how we feel at the end of the class, all right? All right, before we start any new factoring techniques, I just want to bring back factoring just to kind of get the ball rolling. This is what we already know to do. First of all, does anybody remember when you see the word factoring, what does it mean?
I remember you saying
I said it every day for like 3 weeks straight.
No.
When you factor, like, think about it.
It's like something like.
If I ask you to factor 24, what are factors of 24? You got it. Work with me, dear friend. Let me know. Come on. What are factors of 24?
4.
4 and 6. 2 and 12.
24 and 1.
24 and 1 and 6 and 4 if we said it, or 3 and 8. And what do all of those numbers do to 24? They multiply to equal it. So when you factor 24, you broke it into pieces that multiply. That is exactly what factoring means. If you're going to factor something, that means break it up into pieces that multiply. You guys were supposed to remember that. I told you that you have to know what the word itself means.
I said pieces.
Yes, that's true. Break it up into pieces that multiply. That's exactly what you are trying to do when you factor. You got to break it up into pieces that multiply. All right, so let's factor some quadratics. Let's get used to what we've already learned how to do. So if I asked you to take a quadratic expression, degree 2, you got your ax squared, you got your bx, you got your c. This is a normal quadratic expression. If I asked you to factor it, break it up into pieces that multiply to equal it, the first thing you would do is look for a what?
GCF.
What does an x squared, an 11x, and a 24 have in common? Nothing. So that means there is no greatest common factor. You're allowed to break it up into factors right away. Just break it up into its 2 factors. So it's kind of like, if you remember, undoing the FOIL. And we saw that when we were foiling, we know that whatever you put in the first 2 spots always had to multiply to who?
11.
No. X squared. So what can you put here and here that will multiply to x squared? Lock them in, x and x. Now, not only do we want x and x there because they multiply to x squared, we also need them here so now our rainbows can add up to an x term. That's another reason why we need those just x's. All right, now we know whatever number we put here and whatever number we put here has to multiply to who?
11.
No.
Negative 11.
No, 24, and then your rainbows have to multiply and add up to which number? Negative 11x. That's our goal. So you are only allowed to put numbers here that multiply to 24. So it's not like you have a ton of options. It's not like you can just pick your favorite numbers. No, they have to be numbers that multiply to 24. Does anybody have a pair they like if we're trying to get 11?
8 and 3.
8 and 3.
6 plus 40%.
Yeah, we're trying for an 11, Jake. All right. So 3 and 8 in any order. Now we would have 3 times x is 3x. X times 8 is 8x. They could add up to a negative 11. Now you gotta put the signs in, just make sure the signs work, because sometimes it looks like you have it, but the signs don't work. What do you got, Jake?
Both need to be negative.
They both need to be negative, right? The only way you'll get these numbers to add up to negative 11, but still multiply to a positive, is if they are both negative. So we'll put in a minus and a minus. Do you guys remember doing that?
Yeah.
That's how we learned how to factor a quadratic, these degree 2 expressions and equations. All right, let's try one more quadratic before we see a new technique. All right, let's try this one. If you were asked to factor this, break it up into pieces that multiply. First, you'd look for a GCF. Does a 3x squared, a 5x, and a 12 have anything in common? Nope. So that means you can break it up into two factors right away. We know whatever we put in the first two spots has to multiply to who? 3x squared. Who are the only whole numbers in the world that multiply to 3?
3 and 1.
So lock them in. You need a 3, x, and a 1x, right? And again, those x's, they get you the x squared, but they also help your rainbows add up to that x. All right, now I know whatever numbers I put in the last two spots have to multiply to who? No. Right? Remember, Jake, first get you first, last get you last. So I know these numbers have to multiply to negative 12, and then my rainbows have to multiply and add up to who? 5. All right, so let's see. We're only allowed to put numbers there that multiply to 12. What do we got? 1 and 12, 2 and 6, 3 and 4. Anybody have a pair they want to try first?
6 and
6 and 2. All right. Would it be worth it? Would it be worth it to put the 6 here? No, because we've already established that there is no GCF. So don't put a 6 here and create a GCF. So it would only be worth your time to try a 6 there and a 2 there. But guys, if you do that, that's going to get you 2x and 18. Are they going to a 5? So it ain't that. So 2 and 6 are out. It's not even worth switching them because we know the 6 can't go in the other spot. So now you have 1 and 12 or 3 and 4. 3 and 4. If you try 3 and 4, is it worth trying the 3 here? No. So only try the 3 here and the 4 there. Ooh, that would get you a 4x and a 9x. Ooh, they could go to a 5, but again, don't make sure the signs work. If I need to multiply to a negative 12, what kind of signs do I need?
Positive and negative.
Positive and negative. So who should be positive and who should be negative to add up to that 5?
Positive 4, negative 3.
Negative 4, positive that, because they would add up to a positive 5 and they would multiply to a negative. So that means I'm going to need a minus here and a plus there. Is everybody okay? Do you remember doing this? Yeah. Okay. So the first new factoring technique that I'm going to show you guys is going to feel just like this. It's going to be like, this is nice. I already know what I'm doing. There's just one teeny tiny. Are you on the phone? Okay. So now, whatchamacallit, it's going to feel like one little switch that we have to make to do this new factoring technique. So this one shouldn't feel all that different. So the first ones that you're going to run into is they're not going to be degree 2s. We're going to hit higher degree equations and expressions in chapter 5. These are going to be degree 4s. So they're not quadratics, but they're going to factor like a quadratic. These are special degree 4 expressions that actually end up factoring like a quadratic, even though they're not. All right, so I always call these are like quadratics. They're not a quadratic. All right, so look here. It kind of looks similar to something that we've already been asked to factor, except this isn't a degree 2. What degree is this expression? This is degree 4. The highest exponent on a variable is 4. This is a degree 4 expression, so it's not quadratic. However, it does look like one. If this was a quadratic, then it would have said this. This would have been a 1x squared. This would have been a 7x. And this would have been a 10. That's what it would have looked like had it been a quadratic. So guys, if it was a quadratic, factor it for me. Factor this for me. If this was a quadratic, we would have put what here and here, because they would have multiplied to x squared, right? So we would have put x and x. And then we would have put numbers here and here that multiply to who? Well, they would have multiplied to 10, and they would have rainbowed to 7. So 5 and 2. Okay. Does everybody agree that's what we would have factored it as if it was a quadratic? Okay, but guys, it wasn't a quadratic. It wasn't an x squared that we were trying to multiply to. It was an x to the 4th. It wasn't an x that we were trying to rainbow to. It was an x squared. So does anybody know one small little change I could make that would make these multiply to an x to the 4th and then make these add up to an x squared term? Put what? Put squares. put x squared. If you make that little tiny change and use x squareds instead of x's, they factor the exact same way. So these are special degree 4s that will factor just like a quadratic, except you don't need x's, you need x squareds. Go ahead, Derek.
That worked for degree 6.
So if this was a degree 6, if this was an x to the 6th and this was an x to the 3rd, yes. If this was an x to the 8th and this was an x to the 4th, yes, it would always work. So these work for even degree expressions where the middle term is half of it. Yes.
Like x to 16.
You could do x to the 8 and x to the 8. As long as the middle term was x to the 8. As long as if this was 16, then he'd have to be half of it, x to the 8. See how this is 4? That's half of it. It would have to be half of that leading degree. Yes.
Is it always going to be like 4 and 2 or 8 and 4?
I honestly, I don't think when we're in chapter 5, I don't think we see degree 6s like this. So the only ones you will see are the degree 4s. There are degree 6s and 8s out there that factor like this. You're just not going to see
Like,
them.
will it always be a 4 and a 2?
The ones that I give you,
Yeah.
not all degree 4s. If it's a degree 4 that factors, then yes, it'll be a degree 4, degree 2.
Okay.
All right, but we will see other degree 4s, but they're gonna have, if it's a different degree 4, it's gonna have an x to the 3rd and an x. It'll have a lot more terms in it. It won't look like a quadratic. Yes, go ahead.
Is it literally like the same thing? So
It is the same process that we're gonna go through, except all we're doing is using x squareds instead of x's. These are special degree 4s. Again, let me say it. Not all degree 4s are gonna act like this, but these are the special ones that look and act like a quadratic, okay? All right, let's try it again. Look over here. That is a degree 4 expression that we have been asked to factor. It's not quadratic. Man, if it don't look like one. It's got the x to the 4th, and then the x squared, and then the number. So the first thing you would do is you would still look for a GCF first. Does an x to the 4th, a 3x squared, and a 28 have one? No. So let's go right to some factors. And let's say, what could I put here and here that would multiply to x to the 4th, but still get my rainbows to add up to x squareds? X squared and x squared. So we're just going to use x squareds instead of x's. Now it's back in business. Whatever number you put here and whatever number you put there better multiply to negative 28. And then your rainbows better multiply and add up to who? 3x squared. So guys, think about it. What numbers could you put in here that multiply to 28? 7 and 4. I like it. 7 and 4. Doesn't matter the order. And now, what signs do I need if I have a 7x squared and a 4x squared? I need them to add up to positive 3, but I need them to multiply to negative 28.
plus 7 try.
Plus 7 and minus 4. I like it. That would add up to a positive 3. So I would need a plus, and then I would need a minus. Done. Okay. Now, let me throw a little bit of a curveball at you. In chapter 5, if you needed to factor this and you can get here, you're golden. That is perfect. That's really all I need you to be able to do. However, in terms of this being factored completely, you're not done. It does factor again because you're not left with linear factors. You're left with quadratic factors. Quadratics might factor again. Does anybody recognize who that is? He's the difference of perfect squares, and they always factored again. So technically, to be in completely 100% factored form, x squared plus 7 stays, but that factors again. Now there's 2 ways to factor the difference of 2 squares. You can go through your motions and say what times what gets you x squared, what times what gets you negative 4, and then what rainbows to 0 x's in the middle. Or I tried to show you guys a really quick shortcut to squares. Just take their square roots. What's the square root of x squared? X. What's the square root of 4? 2 and 2. And then what signs do you need them to be to multiply to a negative 4 and add up to 0 x's? Plus and negative. So that would be technically what you would want to do if you needed to be 100% factor. But I'm being 100% honest, in chapter 5, if you can just get here, we'll be golden. If you can get here, you'll be fine. But this is truly how he gets factored completely. I'm not going to mark you wrong. When we're working in chapter 5, if you get here, you're good. You're going to get everything that I need you to get. All right, let's try another one. Let's try 3. So look at 3. Again, it's another degree 4, but it kind of looks like a quadratic. So let's see if we can factor it like a quadratic. I would look for a GCF, but does it have one? No. So let's go right to the factors. So we know whatever we put here and here has to multiply to who? 2x to the 4th. Guys, what are the only whole numbers that multiply to 2? 2 and 1, so I need a 2x and a 1x squared. Exactly. Just like before, except now we need x squareds. All right, and now whatever number I put here and whatever number I put here better multiply to -20, and my rainbows better multiply and add up to 3x squared. All right, anybody know what numbers that multiply to 20 you want to try first? 10 and 2? If you try 10 and 2, if you put a 10 here, is that good? If you put a 2 here, is that good? It ain't 10 and 2.
Yeah.
5 and 4. If you try 5 and 4, is it worth putting the 4 here? No, they'd have a GCF. So let's put a 4 here and a 5 there. 5 times x squared is 5x squared. 2x squared times 4 is 8x squared. Oh, I like. But remember, sometimes it looks like you have it and the signs don't work. So just make sure the signs will work. We are trying to multiply to a negative. So what signs do I need?
Positive and negative.
Different signs. Who needs to be positive and negative to add up to that 3?
Positive.
There you go. They will add up to 3, right? I know. You usually want the bigger number to have that sign because you keep the sign of the bigger number. All right, and then what means we'll make it minus, and then we'll make it plus. Okay. Now don't fall for anything. This is not the difference of 2 squares. 2 is not a perfect square. 5 ain't no perfect square. That is not the difference of perfect squares. This one, x squared, is a perfect square. They're just people. It's just people. This is x squared. This is a 4. Those are perfect squares. But guys, is it the difference of them? No, this is the sum. The sum of 2 squares never factors. There's no signs that you will get to do what you need it to do. So that just stays x squared plus 4. This doesn't factor in any way, shape, or form again. All right. I want you guys to try the last one. Factor this one.
Sorry, I have something to say real quick.
Yes.
Dr. Gilman told me I should quit hockey.
No.
Like, I swear.
Why?
Have is like one
Doesn't mean you have to listen.
He
It's
said
just-
he said I should quit hockey and focus on school. But I told him I was like the only thing I'm decently good at is hockey, so why would I quit?
I would never tell you to quit anything that you like and are good at.
He's so weird.
Well, maybe he's just trying to emphasize that school should be your number one priority.
Yes, because I'm gonna use Kevin in the real.
You might use this, Jake, and you're sitting at a red light somewhere and want to factor something. I don't know. All right?
I'm gonna have math weight for my
That's right.
You only have like one thing to do.
Yeah.
It's like,
Yes. Try to factor this though. While we're here, we might as well learn something. Nice.
Yeah, you got it.
Wait, 20
Yeah,
numbers.
Think of numbers that multiply to 18.
Wait.
That's
No, 9
20.
and 10. Bro,
Yeah,
I
but-
didn't want to.
But remember, it's a 3x to the 4th, so it won't just be xx. There's going to be a 3 in front of there that you're going to use with your rainbows. Jake, did you do this? Come on. No, you're not. Did you get it, Chris? Come on. Did you do it?
Having enough to break down.
Stop.
Oh my god, it is nice.
Wait, the last has to equal 18, right?
Yes. Last, first go to the front, last go to the last, and then the rainbows get you the middle. Yeah, awesome.
Oh, listen.
Oh
Yes?
Sorry, what is this?
What? I would first definitely keep looking for your greatest common factor. It doesn't have one. What did you guys put in the first 2 spots to get you 3x to the 4th? 3x squared and
-2.
x squared. And then what numbers did you use that multiply to 18?
-2 and -9.
9 and 2. I would not put the 9 there. He'd have to go here. And then 2. And what signs made them add up to -29?
Oh.
Negative.
Oh, you're right.
Are they both negative?
Yes.
I suppose
yeah,
my
here.
Okay. Yes. Yeah, I'm gonna start the next one though. So this is gonna, I'd look at that one.
Yeah,
Now, does anybody recognize what x squared minus 9 is?
Oh, it's
He's the difference of 2 squares. So again, I'm happy if you're here. But if this was a strictly factoring problem, you would be expected to know to factor that again into, anybody know his factors? X
X3.
plus 3 and x
You
minus
don't
3.
have to do that, correct?
You do not. It will not hurt you in chapter 5. But again, if this had just been a factoring question, that would be expected of you. All right, now, here we go. This technique is gonna be very different for anything I've shown you. Some students like it though, because it doesn't take any of that, oh, what numbers multiply and then rainbow to this. You don't have to go through that process with this. This is strictly gonna come down to greatest common factors. But it's definitely a different process than what you've been used to. All right, now before you say, I don't like it, I don't get it, what the hell did you just do? You have to let me get through 2 examples. You have to see it twice. All right, we're gonna see it, it's gonna be weird. We're gonna try it again, and then you're gonna be like, all right, that might not be that bad. So don't complain until we've done at least 2. Here, go, Jacob, we're not complaining until we do 2. All right, so here we go. This is gonna feel very different.
Oh boy.
Now, truthfully, some Algebra 1 teachers will teach you to factor quadratics this way by grouping. I don't believe it. I don't think you should have to do this unless you absolutely have to. I am a firm believer in the guessing and checking that I taught you. But this is a method called factor by grouping. When you are going to use factor by grouping, you should look at it, and the biggest hint is that there's going to be 4 terms. Normally, when we factor a quadratic, there's an ax squared, a bx, and a c. There's 3 terms that you have to worry about, right? The big giveaway that you might want to try factor something by grouping is that it has 4 terms. Now, you might get to pre-calc, and sometimes it has 6 terms, or 8 terms, or 10 terms. The key is it has to have an even number, 4 or bigger. You should only see the ones that have 4 terms. That's the only ones that you should probably see in chapter 5. All right, so no. Honestly, Jerry, you really don't even see those that often. So here we go. If you're going to factor this by grouping, it's literally what it says. You should notice that this has way too many terms in it to try your normal, what multiplies to this and what rainbows to that. Can't do it. So we're going to try factor by grouping. To factor this by grouping, first, as always, you would look for an overall GCF. It does not have one. So now we go to the factor by grouping process. To factor by grouping, you need to make groups. So you're going to group the first 2, and you're going to group the second 2. And you're almost going to split the problem in half and make it 2 separate problems. Now, in order to group it, you do want it written in descending order. Y to the 3rd, y squared, y, just number. Normally, it's given to you in that order, but if it wasn't, you might want to rearrange to get it in the proper order. All right, once you group it, we are now looking at 2 separate problems. So only look at the first group right now. Do not look there. Just the first group only. I want you to find me the GCF of just this group. What does a 3y to the 3rd and a y squared have in common?
Y squared.
Take it out. If you take a y squared out of this group, I want you to show me what's left. What is left of this group if we pull a y squared out? Well, guys, y squared times what gets you back to 3y to the 3rd? 3y. Y squared times what gets you back to a negative y squared? Negative 1. Perfect. Close catapult. All right, so you have taken the GCF out of the first group. Now we're going to go to the second group. Go ahead.
Sounded like
Close catapult. Yeah, it's
the Sandlot.
the Sandlot. That's what it's from. And I'm so happy. So people have never even seen the Sandlot.
Yeah.
That's crazy. You should not admit that. That is your homework. You should watch the Sandlot. That movie is classic. All right, now, when you go to the second group, we're going to do the same thing. We're going to find the GCF of the second group only. But when you go to the second group, you have to start with your leading sign. Whatever that leading sign of the second group is, you have to pull it out with your GCF. So since it leads with a plus, our GCF is going to be positive. If it led with a negative, our GCF would have been negative. You get the sign just from the leading one. All right, now I want you to find what's the GCF of a 9y and a 3. A 3. So we're taking out a positive 3. If you take out a positive 3, what's left? And this is where, the magic should happen. 3 times what gets you back to a 9y? A 3y. All right, 3 times what gets you back to a negative 3? Okay, so this is how you know factor by grouping just works. Because just because it's 4 terms doesn't mean you can always factor by grouping. It means you can try. This means it worked. You have to end up with this common parenthesis, the same parenthesis. So basically what you've just done is you had this and you had this. You have just created a common factor. They both have a factor of 3y minus 1. So to create your factors that we need, The one they have in common, take it out. That's something they have in common. That's one of our factors. So now when you take that out, what's left? Plus 3. That is your second factor. Don't complain. BB3? Hi. You're fine. Bianca, they have your wallet and keys in the office. Do you know that?
Yeah, my dad dropped it off.
Oh, her dad dropped it off. Yeah, she'll be down. Okay, back. They have them on the counter. I thought somebody found them. They did too. All right, so again, basically, what just happened is you've created a common factor. You take it out, that's always one of your factors. When you take that out, what's left? The GCS, y squared plus 3. They will always make up your second factor. So the parenthesis that matches is one of your factors. The GCS you pulled out is your second factor. I know that feels weird. It's like, how did that just happen? It happened because you created a common factor. You factored it out and you showed what's left. No complaining. Let's try it again. Let's see that again. Let's see it another one. Let's see how it feels if we go through those processes again. This is your final answer.
Yeah, but like, how does the 3y get to the 3y?
Wait, how does what?
Yeah, how does the 3y?
Because you have this, and what does he have as factors? He has a y squared and a 3y minus 1. And then you have this. What does he have as factors? A 3 and a 3y minus 1. They have a factor of 3y minus 1 in common. So I took it out. If you take out their common factor, what's left? A y squared plus a 3. It's like factoring out a GCF. They have a factor of 3y minus 1 in common. 3y minus 1 times this gets you back here. 3y minus 1 times this gets you that. You've taken out a greatest common factor. At the end of the day, all you need to know is that the parenthesis that matched is one answer, and the GCFs you take out is your second factor. That's literally how they get made every single time. Let's try it again. Let's see it again. You got to go through the process. All right, so let's look at this one. If you were asked to factor that, right away you should see 4 terms, say, wait a minute, that's way too big to factor like a quadratic, right? So let's try grouping. It has 4 terms. It does not have an overall GCF, so let's go right to the grouping. Let's group the first 2. Let's group the second 2. And we're going to treat them as 2 separate problems.
Why though? On the left have y squared as the first one.
Because what is a 3y to the third and a y squared in common? He's got 3 y's, he's got 2. They both have at least how many y's? 2. It's always the littlest variable. All right, so now let's look here. The first group, what is their GCF? What does a 2x to the third and a 3x squared have in common? Take it out. If you take an x squared out, what's left of that first group? X squared times what gets you 2x to the third? 2x. And then x squared times what gets you back to a negative 3x squared? Negative 3. Now guys, remember, now you know if factor by grouping is going to work, you need that matching parenthesis. So now you know what you're aiming for over here. Don't force it, but let it guide you. All right, now we go to the second group. You have to pull out the sign, the leading sign. Now I need the GCF of a 50x and a 75. What's the biggest number that will divide evenly into a 50x and a 75? 25. So make it negative 25. And now what's left? Negative 25 times what gets you a negative 50x? Not negative 2x, a 2x, right? Because a negative times a positive gets you back to that negative. Negative 25 times what gets you back to a positive 75? Negative 3. Did it match? Yes. So you've created a common factor. This and this have a factor of 2x minus 3 in common. So take that. Go ahead, Darren.
See how like your top right, what do you call the same one thing?
Catapults.
Yeah.
By parentheses, yeah.
Yeah,
By
the
back.
top one. Yeah, like mine's like I did it like as the before the 50, so it would look like it was like
No, always include his sign. So that's what you know what sign you're taking out with it. So always include his sign in that group. All right, so now this matched. So this is going to be one of your factors. They have a factor of 2x minus 3 in common. If you take that out, what's left? X squared minus 25. That is your second factor. That's your answer. That is factor. That is all I really need you to do. Except, anybody recognize what that is? That's the difference of two squares. That can be factored again. Do I need you to be able to do that? No, it's not necessary. In chapter 5, it will not matter. But if you recognize it, then I would love for you to factor it, just so you know that it's in complete factored form. All right? But at the end of the day, if you can get here, we're golden. Question, Paul? All right. All right, let me try to do, I got time. All right, let's try to do this one. Let's just keep going. You got to keep seeing the process. So right away, if you were asked to factor this, I would look for a greatest common factor. They don't have a GCF. So now I'm looking like, how do I want to factor? How do I want to break this up? It's too big for factoring like a quadratic. It's got 4 terms. So let's try grouping. Let's group the first 2. Let's group the second 2. And now we'll treat it like 2 separate problems. All right, first group. What does an 8x to the third and a 12x squared have in common? A 4x squared. Take it out. All right, what would be left if you took a 4x squared out? 4x squared times 2 gets you 8x to the third, 2x. 4x squared times what gets you positive 12x squared? Plus 3. And now again, use that to guide you. If grouping works, that's what you need left in the next parenthesis as well, but don't force it. All right, we got to pull out the leading sign, so we got to pull out a negative. And now I need you to find the GCF here. What does a 2x and a 3 have in common? Nothing, right? But
-1.
everything has a 1 in common. And you can't pull out 0. You can't pull out nothing. So if there is no GCF, you're going to pull out a +1 or a -1. So in this case, we're definitely going to pull out a -1. You have to pull out something. All right, so if we pull out a -1, -1 times what gets you back to a -2x? A 2x, which is, go ahead, looking good.
It's a 1 of -1.
Remember, it doesn't matter what their signs are, you just pull out the leading one.
Oh, so it's like, if it was a positive 2x, it'd be positive.
Right, if this was a +2x, that would be +1. You don't have to worry about getting a GCF from the 2 of them, you just take the leading sign with your GCF. All right, and then -1 times what gets you -3? +3, there it is. So now it worked, you ended up with that matching factor, that matching parenthesis. So one factor will be 2x plus 3, and then if you take that out, what's left? 4x squared minus 1 is your second factor.
I literally got it.
Now, does anybody recognize what 4x squared minus 1 is? Here's the difference of 2 perfect squares. 4 is a perfect square, x squared is a perfect square, you are subtracting them, and 1's a perfect square. So technically, this should factor, oh yeah, take the square roots, 2x and 2x, and then the square root of 1 is 1 and 1, and we need plus and minus. Again, if you get here, I'm thrilled. If you get there, fabulous. Is it necessary? No. If you can get this, though, from the grouping, that's really all you're going to have to do in chapter 5. All right? How do you guys feel? Okay. I feel better at least having shown you that, so now when we have to use it in chapter 5, I don't have to, teach you in the middle of a section how to do that. All right? So again, after school, I'm going to post an optional homework. Guys, you can literally open it up and do one and say, you know what, I'm good. It's up to you. I'm probably not even going to look at it. It's just there if anybody wants to practice this, because we are definitely going to use these skills. All right.
I said, hey,